All right, electrical fields. I'm going to define, well, electrical fields are defined as the force on a positive test charge. Okay, and fields were studied pretty thoroughly by a man named Faraday. And what he said is that these electrical fields they expand outward from every charge. So if I have a charge here, we draw fields with lines. So there's these lines that extend out in every direction from the charge. Now you'll notice that closer by, the lines are a closer distance between each other, and then the further you go away, then that distance between them gets bigger and bigger and bigger. That means that the electrical field is greater when it's close to the charge. Now, also, if it's defined as the force on a positive test charge, depending on what this charge is, if I put a charge somewhere near, so if I put a positive test charge here, it's going to move depending on what this charge is. So over here I've done an example and I screwed up here, so just don't pay attention to that. If I put a positive test or a positive charge here and I start putting some test charges out there, if I put a test charge here, everywhere in this particular circumference around this test charge, this is where the field lines would be closer. Therefore, if the field is greater, then the force that it supplies on this positive test charge would be a greater force than if it, say, was further away. The further away I get from the charge, the smaller the actual force is going to be. Okay, so I've drawn ones that are along this ring having a greater force than the ones along this ring. They get a smaller force. Okay. Now, I'd also like to point out some similarities here. Electrical fields are very similar to gravitational fields. We described the gravitational field strength, G, as being the force over the mass, and this stems from F of G is m times G. Electrical field is very similar. Instead of a G, that we use an E. That makes sense. Gravitational field, electrical field. It's still got a force, except now that force isn't acting on a mass. The force is acting on a charge. So the newtons for an the units for an electrical field are newtons per coulomb. The force on a charge is equal to the electrical field, like the gravitational field, times the charge instead of a mass. So there's some similarities there. We can also write electrical field strength in terms of Coulomb's law. We had F is K Q1 Q2 over R squared. If we substitute in EQ for F, okay, if we do that little substitution, then we can get the electrical field in terms of KQ over R squared. Okay. The other thing, I want to just kind of go through some pictures with you. Field lines are always drawn away from positive charges, because again, we describe an electrical field as, define it as the force on a positive test charge. So we always draw the field lines away from a positive charge towards a negative charge. They are drawn so that they indicate the direction of the force due to a field on that positive test charge. So if I had a positive charge here, then the field would be going away from this positive charge. So if I put a positive test charge out here, if I put one right here, it's going to go this way. It's going to get pushed away. If I put a positive charge around a negative charge, a positive test charge, it's going to draw it towards it. Okay, this negative charge, the field lines are always aimed towards a negative charge. Okay, so a couple rules here. It says the number of lines is proportional to the magnitude of the charge. So I've drawn equal amounts of lines on here, so chances are maybe this is a +1 Coulomb charge and this is a -1 Coulomb charge. Okay. Also, lines are closer. When lines are closer together, that's where the field is the greatest. Now, I've done some drawings here, and you're going to see some of these. But if I had a positive charge and a negative charge, okay, the positive, if I threw a positive test charge in here, it'd get pushed away from the positive to the negative, so it would get pushed this way. And then the field lines, you'll notice that they kind of spread apart. And you've probably seen this with iron filings and a magnet before. It's very similar. If we had two positive charges, it wouldn't want to go anywhere in here if you put a positive test charge. So you notice that these lines are curling away from each other. They don't actually ever want to touch in that case. And now I've given another one down here where we've got a negative charge and a positive charge that's twice as large as this one. Now, I probably should not have put this line in here the more that I think about it. Okay, but if there were 6 lines going from the positive to the negative, okay, but this is twice as big, then there's 6 lines extending away that aren't touching the positive. This is the part where it says the number of lines is proportional to the magnitude of the charge. If this is twice as large, it should have twice as many lines, field lines, coming off it. Okay, so these are just some basic pictures of electrical fields, and we'll of course dive more into solving some things and drawing some pictures as we go.